So one thing before I continue is I would like to discuss a bit, just very briefly, why is one interested in this exact or total differential at all. So many times in study of thermodynamics we're interested in very small changes of some quantity like the inner energy or work or entropy, and actually the total differentials are used to describe changes in these quantities. Mathematically they were useful, and sometimes or in the study of thermodynamics one has to distinguish between the exact or total differentials and the inexact differentials. But if you just have now derived an expression from very small changes of a quantity, but if you want to describe bigger changes, which is often necessary, or almost in every case, we have to integrate over this quantity. So what happens when integrating df? So I write down again the formula we had found in the last video. So df equals df over dx times dx plus df over dy times dy. And integral symbol here, and notice that this expression here can also be written in the vector form. So it would be df over dx, df over dy, dx dy. So this is the scalar product, or this is a vector scalar product. And this quantity here is the gradient of is called the gradient of f. So df over dx and df over dy is often written in short notation, f subscript x, f subscript y. And this is the gradient of f. So actually, why is this useful in our discussion? I decided, or for me it makes sense to go this way to make sense of what integration limits to put here, or over which quantity we are actually integrating over. So far, that's not quite clear how our integration boundaries should look like. For this purpose, let's consider the function we had again in our last video. And let's call our function f of x and y. Make a specific example. It's minus 1/2 x squared minus 1/2 y squared. So this function pretty much looks like our hat from the last video. Maybe it looks like this. Scroll it. Looks something like this. Here would be the x-axis. Here would be the y-axis, and the z-axis goes in this direction. The top of this curve it is at the 0, 0 point. Now let's calculate the gradient. What does the gradient of this function look like? minus x and minus y. So how is this useful for us now? Note that here we would like to sum up over infinitesimally small scalar products. Keep this in mind now, and also note that this quantity here, the gradient, is defined at every point in the xy plane. So this means that we already know we have to find our integration boundaries in the xy plane. Somehow we can ignore here for the integration boundaries the z-axis dimension. For this purpose, I draw again here the xy plane. And let's say here would be 1, 1, minus 1, 1. And if I draw the vectors, it turns out that here at the 1, 1 point, the vector which is defined at the 1, 1 point, so x is 1, y is 1, so the vector is the minus 1 vector pointing in this direction. So I can go on like this. All vectors here that point to the center. This is actually also called, in case one does not know, a vector field of the function f. And let's say if one moves outward, the length of the vectors, they increase. So if we start at the, for example, point 2, minus 2 should be here, we would move also inward to the center. Now we know, okay, we have a bunch, or at every point in the xy plane there is a vector defined by the gradient. And we would like to sum up the scalar product of the gradient vector with this infinitesimally small vector here that indicates somehow a change. But I can, for example, draw here one vector. Let's say this would be, it's not mathematically strictly correct, but it's just for illustration purposes. Here we move one piece in this direction, then one piece in this direction, then in this direction, then in this, and at every point here we have a new scalar product, and this contributes to the sum here we are interested in, or the integral. Therefore, actually what we are integrating over here is the integral over a curve. And before I will go on and explain how to calculate this, let's already write a C here for curve. And before I move on, explaining what actual values can be set in here for the integration boundaries, I would also like to mention that this has a physical equivalent, or also a sort of a physical interpretation. If the vectors here actually describe a force, then let's say we have at every point of the plane a force vector, and we multiply it with some infinitesimally small change, which would be our dx dy vector. And if we integrate over this infinitesimally small vector product or scalar product, then we get the quantity work, physical work.